Okay, with this video, we're going to begin our study in rotation. And rotation is going to be the first unit that we do not go slowly through the four perspectives. We're going to move rather quickly through the four perspectives to study this one phenomenon of rotation. Prior to this, as we were learning the four perspectives individually, we really slowed down and we took our time and we studied kinematics and then forces and then work and energy and then finally impulse and momentum. But all we were doing was studying one particular phenomenon, and that was translation through space, not rotation. And so this is the unit where we get to put it all together and work more quickly through the various phenomenons of nature using our four perspectives. So the first question I want to present you with is the one where we take a rubber stopper tied to a string, or maybe you have keys on a lanyard, and you're just going to spin it in a vertical circle, just because you're sitting there bored. And my question to you is that rotation, or is that just circular motion like we studied before? Okay, so you may have had a hard time answering that question, and it would be a tough one. I mean, it really is a tough one when you don't have a definition for rotation. So let's define what rotation is, and then see what you think after we put up a definition. Okay, so here's our definition for rotation, or how we're going to know that we observe a rotation. And that is that all points on an extended body move in a circular path around a fixed point. So let's define what a couple of these terms are. Okay, so an extended body is the first one that we need to pay attention to. And extended bodies are really just any three-dimensional object, which is virtually everything around us. But up to this point, we never looked at anything as an extended body. It was always treated as a point particle. The center of mass is usually what represented the entire object. And now we're actually going to have to pay attention to the whole object. It's not going to be just a part of it, just a point. So that's what an extended body is. Now, the fixed point that you're rotating around, you already know what this is called. You know it from other classes. This is the axis of rotation. So when we look at the example of the keys that are swinging around on a lanyard as you wrap it around your finger, or you just take a rubber stopper and you're swinging it in that circle, maybe you're thinking about the flying pigs, that would be an example. The question remains, are we looking at circular motion or rotation? And the answer to that is, well, both. It can be either rotation or we can treat it as circular motion. So if we look at the rubber stopper as an example, and I'm going to draw the rubber stopper so that it looks something like a wedge. In other words, this top section is wider than the bottom section, and it's attached to a string, and it's just going to move around in a circular path. Okay, so it's swinging in that direction and it comes up from this direction. And what we're going to see is if we look at this point on the particle, it's going to follow that circular path. This point of our object, it's going to follow a circular path just of a smaller radius. And the same thing with that point on the object. It's going to follow a circular path just with a smaller radius. And so that's all we mean. Now, this object doesn't have to only rotate. It can move through space. Maybe you're walking as you're swinging, your keys. And we'll address those as needed. So our primary focus in this video is going to be to just get through the definitions of perspective number 1, which is kinematics. Okay, so we're going to start with the definitions just like we did with kinematics and translation. And the first term we have to learn about is angular position. Now, angular position we denote with the letter theta. And the angular position is not going to be measured in degrees, but it's going to be measured in radians. And the angular position is nothing more than where the object is rotated to relative to a reference line. So what I mean by that is this. Maybe you have a disk and you mark some point on that disk, and I'm going to pick this point right here. I'm going to draw a reference line so that I know where 0 is, 0 radians for our angular measure, and the object is located in that vertical position. Now, you might say that it's located 90 degrees because this would be 0 degrees, this reference line, and because it's pointing straight up, you might say that this is 90 degrees. But we're going to use radian measure for a special reason. Degrees still have units. Radian measure does not have a unit. So to make sure that you understand why this is, let's take a look at the definition of the radian. So the radian, it's given the angle theta, or the letter theta. It is defined by the arc length over the radius of the circle. Now, the arc length might be the line from here to here, if I use this particular circle here, and the radius, of course, goes from the center of the circle out to that edge. So this is the arc length S. Well, the reason we use radians in physics is because S, the arc length, is going to be measured in meters, and the radius of the circle is also measured in meters, and meters divided by meters is just 1. So radian measure is important because it's unitless. Even though we refer to it as radians, it's not actually a unit, and so we don't have to pay attention to that complicating factor. So you already know that 90 degrees is basically pi over 2 radians because a complete circle has 2 pi radians. The arc length would be the circumference, and the radius is just r, so 2 pi r divided by r becomes 2 pi. So we have 2 pi radians in a complete circle. Well, the angular position of our point x right here is just pi over 2. If we put our point x over here, then it would just be pi. And if we put it here, then the position would be 3 pi over 2. Okay, so that's angular position, but the important thing is to notice that the object has not rotated at all at this point in time. It's just a location relative to the reference line. Now, similar to position, just like we had in translation, is displacement. And in angular displacement, instead of using d like we did with translation, we're going to use delta theta. Okay, so delta theta is going to be the angular displacement. It too is measured in radians. And this, if we look at it in terms of time, time has elapsed in order for there to be a displacement. So it's basically how much the object has rotated. Okay, if you notice our definition for angular position, we said how much the object is rotated. Is does not imply that some time interval has elapsed for the position to have changed. But whenever we say how much the object has rotated, that means it has moved because time has elapsed. So, in other words, we start at maybe pi over 2 radians, and if we go to 3 pi over 2 radians down here, then our displacement is going to be from here to here. So the displacement delta theta in this case is going to be just like we have in translation, the displacement here is going to be, by definition, delta theta is equal to theta final minus theta initial. And so delta theta becomes 3 pi over 2 minus pi over 2, or delta theta is equal to pi radians. Okay, and that's just half of a circle, and so that's very easy to see in this example. But the initial position was at pi over 2, and the final position was at 3 pi over 2. So time had to elapse for it to go from point A to point B. The next term on our list is going to be the angular velocity. Now, the angular velocity gets the Greek letter omega, and that will be measured in radians per second. Okay. Now, you want to be careful with how you write omega, because omega looks an awful lot like a W. So you're going to have to figure out how you specifically are going to distinguish between W and omega with your writing. But generally, when you write a W, it's got straight sides. Omega tends to curl in. So you can see there's a visible difference between omega and W. Now, I know some of you are thinking, wait a minute, I thought omega was the horseshoe looking symbol. And you would be correct. The difference between these two omegas is that this omega is a capital omega, and this omega is a lowercase omega. So it's no different than writing capital A and a lowercase a. They look very different from each other. And so that's all it is. Now, the angular velocity is just how fast the angular position changes. And by definition, the average angular velocity is just equal to delta theta over delta t. In translation, what we saw was the average velocity was equal to delta x over delta t. And so one of the things that we're going to see throughout this study in rotation is that pretty much all of our equations that we saw in translation, where this was an example in translation, v is equal to delta x over delta t, we're going to see the analogous form of it in rotation. In other words, it's an equation that has the exact same variables, except instead of using translational variables, we're using rotational variables. For example, this v is the translational velocity, omega is a rotational velocity. So you're going to see this a lot, and that should help you through the unit. Okay, let's take a look at the last of our terms, and that's going to be the angular acceleration. And we use the Greek letter alpha for angular acceleration. Angular acceleration is going to be in units of radians per second squared. And remember that the second squared is a mathematical shorthand, and so we could write this a little differently, and we could say that it is radians per second every second. So if you have an acceleration of 5 radians per second squared, then that means your velocity will change by 5 radians per second during each 1 second interval. By definition, mathematical definition, the angular acceleration is going to be alpha is equal to delta omega over delta t. And of course, you can write that as omega final minus omega initial divided by t, where anytime you see a naked t like that without the delta, it's still representing a time interval. The one last thing that I want to discuss with you before I end this video and move on to the next one is the idea of direction. More specifically, what is the sign convention? Now, the sign convention is this. The positive direction is going to be counterclockwise, and the negative direction will be clockwise. In another video, I'm going to go over this specifically, why it is the way it is. Okay, so if we're looking at a wheel which is rotating, so maybe this is a bicycle wheel or something like that. If the wheel is rotating in the counterclockwise direction, we would say that omega is positive. And if it's rotating in the clockwise direction, then we would say omega is negative. And that's all it means.